So just to recall the last class what we have discussed, in the last class we have seen the Lagrangian multiplier method for generalized nonlinear programming problem. When we have equality more than one equality constants. And then we have also seen the Karush-Kuntakar conditions for nonlinear programming problem with one constraint. And that for a maximization problem, maximization type, problem, we have seen that Karush-Kuntakar conditions that are necessary conditions are this. When it is maximization, is hx is less than equals to 0. And the multipliers, these are the Lagrange's multipliers, are greater or equals to 0. But if we have a minimization, then the functions will be, for minimization, it will be this conditions will be first one to second one will be same. This delta del h del x j equals to 0. Then lambda hx is 0. Then hx is greater or equals to 0. And the multipliers will be less than 0. So that's for minimization problem. So these are KKT conditions. Okay. And then we have seen that these conditions are necessary conditions. Okay. And they will be sufficient also if these functions, the objective function is either convex or concave. And the constraint function must be convex. Okay. But there are functions for which we have seen that if this is a non-convex function, the objective function is non-convex, then we cannot say these are the necessary and sufficient conditions. Okay. So these are necessary and sufficient only for these cases. If the objective function is convex or concave and the constraint function is convex, then we can say that these are necessary and sufficient condition. Okay. So we will see the extension of this approach, the conditions if we have more than one constraint. So if we have more than one constraint, so we need to introduce more than one slack variables. And we have seen this one, just now we have mentioned. Okay. Yeah, that's what the story says this. This objective function can be convex, concave, or non-convex. So non-convex function we have defined that if we have this kind of function. So this is a non-convex function. Take any 2 point. The chord is sometimes it is below the curve and sometimes it is above the curve. So this is not a convex set, neither concave set. This is a non-convex set, non-convex function. Okay then. And then if we have m different.
No, pasó a ayer.
Anyone speaking? Anyone doubt?
10,985.
Brigant, Bhushan,
Sorry, sir. Sorry, sir.
you have any doubt?
No, sir. No, sir. Actu-
Please mute your mic.
Yes, yes, yes.
Okay, so let us discuss. So if we have greater than type constraint, then we need surplus variable. Okay, so there are m different constraints are there. So we need m different slack variables. So this concept we have to extend. Okay, so now we have a generalized function more than one inequality constraint. And in the last class, we have seen this. If we take this SI square, that is square, then this function, this slack variable is nowhere in the conditions. Okay, so we don't have to bother about the S variable. Okay. S is not here. For here also, S is not there. The slack variables are not. They will be eliminated after the computations. So we don't have to bother about it. So that is why if we have this h1x is actually g1x minus b1 less equals to 0. So then h1x plus s1 square equals to 0. So this one our slack variable. Similarly, we have to do for s2. Here we will introduce s2, then and then sn. So m different slack variables will be there, and then we repeat the process. What is the process? We have to define the Lagrangian function. The Lagrangian will be okay. So if you expand this function, then it will look like of this form. And if you just write it in a summation short form, so we'll have to use the summation symbol. So 1 to m, then lambda I hi si square. So this is the function now, or Lagrangian function, augmented Lagrangian function. Now what we have to do for finding the necessary conditions, we have to find out del L by del X. Here X means, sorry, this is X n. There are n variables. Okay. There will be n variables. So this is X. Del L Xj. We'll make it 0. And del lambda I equals to 0. I belongs to, I varies from 1 to m. And then del L del S I varies from 1 to m. So we'll make it 0 and then we'll try to find out the equations. So once we do this, so first necessary condition is this one. Then the second necessary condition is this one. We make it 0. The third necessary set of conditions are this one. Now if you look at this, we have to, this condition 2 and 3 can be replaced for the following set of conditions by carrying out the similar analysis that we have discussed. That means if we consider all the lambda i's are greater than 0, the product of two lambda i's are, it can be 0, it can be non-zero also, it can be negative positive. Okay. Right. But SI square, SI we have taken as greater or equals to 0, slack variables. Okay. Slack variables we have taken greater or equals to 0. So in that case, what we have to take? Either this lambda I greater than 0 or lambda I less than 0. This can be the case. So if you, from this case we go here and then do the similar analysis that we have done in case of one variable, the problem with one constraint. So this equation 2 and 3 will be reduced to these equations. Okay. So lambda I is equals to 0 and then lambda I into hi. This. So if you just accumulate all these functions, then and try to write down the Kuntakar conditions for a non-linear programming problem for maximizing effects subject to the constraints. So this is a generalized version. We have now m different constraints. Okay. So this is for maximization problem. These are necessary conditions and they will be sufficient if the objective function is convex or concave. This is maximization, so that means concave. And the multipliers will be positive. Lagrange multipliers. Okay. So similarly, we can have another set of necessary conditions for which we have multipliers will be this time negative. Okay. So these are negative multipliers. So in this case, once again, if the function is a convex or concave, the concave or convex, fx is convex or concave, then these functions will be sufficient also. These conditions will be sufficient also. Not only necessary, they are sufficient also. And the set of constraints, HIX, all have to be convex. This is actually, it should be convex. HIX are in convex set. So this is a mistake. Okay. Now for both cases, we will discuss. Not only both cases, we will see one example. We have less than type criteria, constraints are less than type, function is maximization type. So we have to maximize this nonlinear constraint function. So for that, what we have to do? We have to define the Lagrangian. So what will be the Lagrangian? Okay. In fact, if you see there's functions, we don't need the Lagrangian anymore. See here, it only depends on f, h, lambda. It is not depending on the Lagrangian function. Although we are taking help of the Lagrangian, but after finding the conditions, we don't need them anymore. We don't need this L anymore. Okay. Once we have the criteria, once we have the, we derive these conditions, then we can directly apply these conditions here. So fx is this one. We have fx. F of x is this function, and then h1x and h2x is this one. So m equals to 2 here, and n equals to n equals to also 2. Okay. So what we do is we find the first set of differential condition, first set of what is it called? Kuntaga conditions. We satisfy this one and try to find out all this equation. Del f, del x. If you try to find out del f, del xj. So first we will write del f x1, del x1. So if you define it, so this would be 14x1 plus 6, and then this is x2, so this would be 0 plus 0. So let us not write. Then del f del x2. What is it? It is only 10x2. Then what we have to do? We have to satisfy this equation. So for that we have 14. Also we have to find out h1 h2x. So del h1 del x1. So this is 1, and then del h2 del x2. So this is again, so this is right, so the 1. So this is again 2. So this is 2. So if you try to find out, this equation is actually del f del x1 minus lambda 1 times del h1 del x1 plus, not plus, let us write minus lambda 2 del h1 del h del x2, and this is 0. So we can have this one is, so this is 14 plus 6 minus lambda into 1 minus lambda into 1, lambda 2 into 1. Okay, so this is lambda 1 into 1. This is lambda 2 into 1. And this is 14x plus 6. So here it is. Similarly, we can do this, all the computations. And then we try to find out the equations. Now the next task is to find out what will happen if there will be 4 cases, since 2 different cases are there, lambda 1 and lambda 2. So we have to investigate them separately. If both of them are equal to 0, let us consider this case. Then what will happen? I put 0 here, 0 here. So this will give you 14x1 plus 6 equals to 0. So this is x1 equals to 6 by 14. So 3 by 7. In fact, negative will be there. Okay. And then from here, the second equation will give us 10x2 minus, okay, equals to 0 if lambda 1 and lambda 2 are 0. So this will imply x2 equals to 0. Is it a feasible solution? No, because we have x1 and x2 greater or equals to 0. So this is not a feasible solution. Here. So the first case that both are 0 is not considered as a feasible solution. So they cannot give the feasible solution. Okay. Now what about the second case? If we have the second case that lambda 1 0, lambda 2 non-zero. So in that case, if this is the 0, so it becomes 0, and then this becomes non-zero. But if this is non-zero, lambda 2 non-zero, so this will become 0 because the product of two quantity is 0. So one of them is non-zero, so the other part is 0. Okay, right. So we make it 0, and then we try to find out the other quantities. So from equation 4, we have this relation, and then from 1 and 2. So these two equations, we have 14x1 plus 6x plus 6 minus lambda 2 equals to 0. Why? Because we have assumed that lambda 1 is 0. So this is 0. So this equation reduces to of this form. And then similarly, the second equation reduces to this form. Now what we have? So we have equation 1, this is 2, and then this is 3. We have a system of linear equations where we have 3 variable and 3 constraints. So this is a feasible solution we can find. Now, whether this is a feasible, okay. In fact, we can find this system of linear equation with 3 equation and 3 variables. So we can find it, the solution. Here we can see this is x1 is positive, x2 is negative, lambda 1 we have assumed 0, and lambda 2 we are getting positive. So again, this is non-infeasible solution because x2 becomes negative. If it is a feasible solution, then we have positive. Now we take the case 3 when lambda 1 is non-negative, sorry, non-zero, and lambda 2 is 0. Then what happens? From 1, 2, and 3, we have this is non-zero, so we put 0 here, we put 0 here, again we put 0 here. Okay, and this is non-zero, that means this part will be 0. So we write down this. Okay, we write down this equation here, and then here, and from here we get this. So again, this is a system of linear equation with 3 variable and 3 equation. So you can solve it. After solving, you will get, so you can use the Gauss elimination method. Or you can get a Gauss-Jordan elimination. Okay, so the solution becomes x1, x2, and this is lambda 1 and this is lambda 2. So we can get a feasible solution here. So all the variables are positive. In fact, even if this is lambda 1 and lambda 2 are, in fact, if they become negative, then also we have a problem. because Kuhn-Tucker conditions for a maximization problem, you know that they will be positive. Okay, so that is why we have to take this case. So these are also greater or equals to 0. So this is satisfied. And then we try to find out the z value. The only thing remains, that is, if both are non-zero. If both are non-zero, then what will happen? So in that case, we will have this equation number 1, equation number 2. Then this is non-zero, that means the other part is 0. If this is non-zero, so this part will be 0. We have a 4 by 4 system. 4 variables, 4 equations, 4 variables. So we can solve it. If we solve it, we can see that this is x1, x2, x3 and x4. Okay. Now this computation is little bit difficult because solving a 4 by 4 system within hand calculation, it becomes a little, it takes little longer. So that is why we can take the help of computing tools. So they will give you directly these values. And then we have to evaluate whether this is a maximization. Since this is a maximization problem, we had one feasible solution, but this is not our optimal solution. What is our optimal solution? This one. Because we are solving a maximization problem and maximization happens to be here at this point. So this is how we can use Kuhn-Tucker conditions for nonlinear programming problems with more than one inequality constraints. Now for your practice, I have added some 4 problems. So you have to verify these results. Okay. Now the next topic that we have, it is very closely related to the topic that we have just discussed. Okay. We know that simplex algorithm method cannot be applied to nonlinear programming problems. Okay, but recall that f of x1, f of x, for example, x1 square plus x2 square plus x3 square. Now, if you take this differentiation, if you take the gradient, or if you think that if test, for example, x1 square, let us write x square plus 2x plus 1. So f test of x, what is it? 2x plus 2. So what happens if the quadratic function is given? So this is a non-linear function. Non-linear function. In a specific, more specific quadratic function. nonlinear is a generalized sense because this order can be 3, 4, 5, any order. But we are focusing on only 2. But the derivative is actually now become linear. Okay. So when this linear function we have, we can apply the simplex algorithm. So with this idea, Wolfe has, Professor Wolfe has defined, or he has modified this simplex algorithm to find out the nonlinear uh, quadratic programming, this quadratic function. If remember, this method is applicable only for the function with who have quadratic function. Whereas the highest order of the variables is 2. Highest degree, not order, is 2. So this is a quadratic form, more or less. Okay, it can be if you remember. So more or less here the maximum order is 2, maximum degree of a variable is 2, and then this can be also written as. In fact, so these concepts are actually closely related to the concept of mathematics 1. And then how we call it a positive definite or semi-definite, negative definite, all those criteria are actually written. Okay, so this is positive, negative, positive semi-definite, then negative definite, negative semi-definite. But it is very difficult to find such non-zero vector x so that we can verify this relation. So that is why we had used the shortcut method. Given a matrix, n by n order matrix, we'll find out the minor of order 1. That means the first element A11, minor of order 2, minor of order 3, and so on. If all the principal minors are positive, then we call it. So this is a shortcut method that we have discussed. Now, for quadratic programming problem, the function, the objective function will be of the quadratic nature, and the quadratic function can also be represented in this form. If you just look at C1 x1 plus C2 x2 plus Cn plus Cn xn. Okay, then plus half of, if you write this one, what it will be? So we will have square terms, x1 square when j equals to k, then x1 square into, so d11 plus all other terms will be there, and some dij, then xi xj plus dnn dxn xn square. So each of the term will have maximum degree 2. So here is degree 2, here is 1 plus 1, this is also degree 2, here is degree 2. So for quadratic, more generalized function is represented in this form. And the constraint function that we have are actually linear type. Okay, this is non-linear. Now if we differentiate, then the function f dash becomes linear because this is a quadratic function. So f dash becomes nonlinear. But for a nonlinear function, we have seen that we can use Kuhn-Tucker conditions for a necessary and sufficient condition. So similarly, we have to define the Lagrangian function. Now we have set up all the variable. So this is xij greater equals to 0, and then we introduce slack variables. This is also slack variable. This is surplus variable rj, and then we write the Lagrangian function of this form. Now we have to take that x is our, how many variables are there? N variables. Now this is slack variables. S is slack variables. S1, S2, Sm. What is M or N? Okay, yeah, M. What is R? R is the surplus variables. R1, R2, Rn. Then it is lambda. Lambda is there. Lambda 1, lambda 2, lambda n. And then there are some constraints, some multipliers which are mu, or mu1, mu2, this is mu n. So all these are unknown. We have to find out them. So we take the help of calculus and make them the necessary conditions as 0, and then we simplify. So after simplification, you please take care of this. Okay. There it will be used. So whether this is sufficient or not. Okay. So from equation 2 and 3 here, this case, and this is the case of 3. Use complementary slackness property. Conditions. If we use them, then it will be reduced to the conditions. So the function, that is the algorithm, that Wolfe's modified simplex algorithm, will look like this. First, we have to convert the inequality constraint to equations, and then we introduce slack variables. After that, we define the Lagrangian function and derive the Kuhn-Tucker condition. So derivation of Kuhn-Tucker condition is expected. Those who are starting this optimization technique and they are starting this nonlinear case, they must know what are Kuhn-Tucker conditions for a given problem. It is like if you visit Kolkata, people will ask you, have you did you have Rasagolla? Yes, same. Okay, but if you visit Chennai, then we will ask you idli sambar. So those who are starting this nonlinear case, it is expected to tell the Kuhn-Tucker conditions. So it is that much important. Then we have to understand step 3. So step 3 we have to introduce, because we will have equality constraints. All are equal. Then we have to introduce some artificial variable to start the basic feasible solution. And then we can use two-phase method. Okay, because the two-phase method is very efficient. If we define the BGM method, then it becomes a difficulty to handle with BGM. Okay, so that is why we will use this method. Now the function remains to minimize mj, and all the criteria, all the conditions, they have become now linear. So we can start the algorithm now. So if you think about this problem, okay, so this is x1 and x2 is there. Then we have variables, because for this we have to introduce slack 1. For this one we have to introduce slack 2, and from there we have to introduce R1 and R2. So let us take the simple case. S equals to S1, S2. R equals to R1, R2. Then we have lambda. Lambda will be lambda 1 and lambda 2. How about mu? So this is mu 1, mu 2. Both of them are multipliers. Okay, so we have to find out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 unknowns. And the Lagrangian function becomes of this form. Okay. Now if you simplify and make them 0, so we'll have 10 equations, 10 linear equations, and then we again simplify it after using the conditions, complementary slackness conditions. So the problem now reduces to of this form. So these are the necessary conditions for this problem. Then you have to redefine the problem. That you have to minimize these functions, and then we find out the x1, x2, lambda 1, lambda 2 values. Okay. So let us start the simplex algorithm. So let us write all the variables. And if you try to find out this, because in two-phase method, what we do, we will take all the variables as 0, and only one will be for artificial variables. So we calculate, here it is maximum Cj minus Zj. So this is a minimization problem, remember. Minimization. If you remember, for Cj minus Zj, we had maximum positive. So in this case, we have to select because these are multipliers, we don't bother about it. We have to find x1 and x2. Okay, so that is why x2 will enter, x1 will enter the basis, and this minimum theta, for that we have to calculate that a1 is leaving, so x1 will come to this place. Okay, and then iteration 2, this is also minimization. But all are not negative. So we'll try to enter with x2, and we repeat this process. So these are still negative. if we will stop here, earlier or the criteria was all Cj minus Zj was supposed to be greater equal, sorry, less equals to 0 for maximization. But if it is a minimization problem, then we can have all are either positive or 0. So in this case, the fourth iteration, we can see that this is positive and all other are 0. And now we can see that x1 is our 2 by 3 and x2 is now 14 by 9. So we can find out the maximum value. So Z max is again this one. Now you can realize that this problem is not, if you do this hand calculation, so it is, it will take too much time, even for a simple problem. So what we have discussed so far, you can see that this is a very simple problem, only two variable and two constants. Now if you have 20 variables and 20 constants, then how we will do? For that we have to design some algorithms. Okay. But the thing is, you have to know how to find out the Kuhn-Tucker conditions. So these Kuhn-Tucker conditions are used to formulate the slack variables. Okay. You can see here, the slack variables are written here in this way, but the slack variables are actually ultimately removed as a linear case. Two, 3, 1, 6. Here, 2, 3, 1, 6. We have to replace this one because we are solving linear case. So S1 square and S2 square will be replaced by the slack variables, because slack variables will not improve the solution. They are just dummy variables in the objective function. If you remember the slack variables, for slack variables, what are the coefficients? 0 S1 plus 0 S2. So they are dummy variables. So that is why these square terms are replaced by S1 and S2 in the quadratic programming or the Wolfe's method. Now this problem we have to solve in this way. So I will add some more problems for practicing your. In fact, you can try this problem, Wolfe's method. I can give you this. Yeah, so let me just copy and then paste it somewhere here. So what we are at present now, because we have only 1 week left for class. In fact, two weeks are there. but I have some work so that I wanted to finish early. So if you remember, for linear programming, we have discussed all these methods. Only the left thing is this is very close to related to, this is not exactly the matrix form of the, this reverse simplex method is very close to the matrix form of the simplex method. Okay, but we don't have that much time, so I'll exclude this method from your final exam. Most interested, I mean, if you are more interested, you can read yourself. And the thing is, I have already discussed this matrix method. So those who have understood this method, they can easily find, they can easily follow this method. Reverse simplex method. So not okay, not for Ian. The only thing that we have so far, so these are linear combinations we have discussed. Then for integer programming, we have discussed all these methods. And then we have discussed the linear programming problems, all the classical methods, and we have revised all them. Then Lagrangian multiplier method, Kuntakar conditions, quadratic forms. Just to recall, quadratic programming structure that we have discussed, and today we have discussed the Wolf's method. The only remaining thing is this one. So we'll try to cover up all the topics in the next week, next 3 lectures. Okay, then our syllabus will be complete. If you have any doubt, you can ask me.